A review of criticality accidents, Part 3, Mayak Production Association, 21 April 1957. Link in the description below. This accident occurred in a large industrial building housing various operations with highly enriched uranium. Operations were being conducted under the 6-hour shifts, 4 shifts per day mode prevalent in Mayak. Rooms typically contain several glove boxes separated from each other by about 2 meters and interconnected by various liquid transfer and vacuum lines. The accident took place in a filtrate receiving vessel that was part of batch mode, liquid waste processing, and recovery operations. A layout of the glove box and its equipment is shown in Figure 7. This was a typical 1 workstation deep by 2 workstations wide glove box. The normal process flow was as follows. The main feed material, impure uranyl nitrate, was generated in upstream uranium-90 metal purification operations. This, along with oxalic acid, was introduced into the precipitation vessel, which was equipped with a stirrer and an external steam or water heating jacket. A batch would typically contain a few hundred grams of uranium feed and about 10 liters of liquid. Concentration was usually in the 30 to 100 gram uranium per liter range. The stirrer operated continuously during the process to prevent the accumulation of oxalate precipitate on the vessel bottom. The oxalate precipitate slurry was then vacuum transferred to a holding tank from which it was drained into a filter vessel. The precipitate containing the uranium was collected on the filter fabric, and the filtrate was pulled through by vacuum and collected in a filtrate receiving vessel, where the accident took place. This vessel was a horizontal cylinder 450 millimeters in diameter by 650 millimeters in length, and had a volume of approximately 100 liters. As indicated in the figure, the filtrate was removed through a dip tube and transferred to an adjacent glove box. A 2-tier hierarchy of procedures and requirements was in place at the time. Upper-level documents described operations covering large work areas in general terms, while criticality guidance was contained in operating instructions and data sheets posted at each glove box. Specifics associated with each batch, such as the fissile mass, time, temperature, and responsible operators, were recorded on the data sheets that were retained for 1 month. Important entries from the data sheets were transcribed to the main shift logs that were retained for 1 year. Operational and fissile mass throughput considerations dictated the design and layout of glove box equipment. Thus, major pieces of equipment were not necessarily of favorable geometry. Limitation of the fissile mass per batch was the primary criticality control throughout the glove box. The procedure called for the uranium-90 mass per batch to be less than 800 grams. The fissile mass was determined from the known volume and concentration of the uranyl nitrate. Historically, this had resulted in relatively accurate fissile mass control. However, in spite of the fact that the operator followed the available procedures and did not violate criticality controls, there were several factors which contributed to the accumulation of uranium far in excess of that expected. The temperature of the precipitating solution was an important process variable, but there was no monitoring device such as a thermocouple. Temperature rise was controlled by the heating time, routinely about 10 minutes. The solution was not brought to boiling. In addition to temperature, the stoichiometry of the solution was important, but control of the uranium concentration was rather imprecise. Therefore, the supernatant, the precipitate-bearing liquid, that was fed to the filter vessel could have had an elevated temperature and/or acidity, resulting in a higher uranium concentration than anticipated. After the supernatant, now called the filtrate, entered the filtrate receiving vessel, it would cool, resulting in additional precipitation of uranyl oxalate trihydrate and its slow accumulation into a hard, thin crust over much of the lower inside of the filtrate receiving vessel. While not known for sure, it was suspected that minor defects in the filter fabric might also have contributed to an increased rate of precipitate accumulation in the filtrate vessel. Procedures called for the filter fabric to be replaced based on either visual evidence of defects or unusually high flow rates through the filter. Operating instructions required a fissile mass accountability balance between the incoming and product fissile streams. If the difference was less than 5%, then the next batch could be introduced into the glove box. But if the difference exceeded 5%, then it was required that the vessels be cleaned out. Operating procedures required that these vessels be cleaned out on a specified schedule. However, there was apparently no limitation on the number of batches that could be processed between cleanings, if the 5% threshold was not exceeded. Also, there was no tracking of the fissile mass as it accumulated between cleanings. There was no online instrumentation for measuring process parameters such as uranium concentration or accumulation in the receiving vessel. There was no operationally convenient way to visually inspect the inside of the receiving vessel. Finally, a likely major contributor to the accident was a procedural change that had occurred 2 months before. In an attempt to minimize personnel contamination and process downtime associated with the previous practice of routine physical and mechanical cleaning of the vessels, it was decided that a simple acid flushing of the vessels would be adequate. 2 months after the implementation of this procedural change, the accident occurred. While not a requirement for criticality control, the radiation control personnel routinely checked for uranium buildup with portable gamma ray instruments from outside of the glove box. They had not reported any increase in the normal background radiation field before the accident. The criticality accident occurred during what was thought to be routine vacuum filtration of a batch of uranyl oxalate trihydrate precipitate slurry. Looking through the glove box window, the operator observed the filter vessel fabric bulge upward, followed by a violent release of gas and the ejection of some of the precipitate out of the filter vessel and onto the glove box floor. The operator instinctively gathered up the precipitate by hand and put it back into the filter vessel. Immediately after, seconds, not minutes, the operator began to feel ill. The release of gas or vapor continued for about 10 minutes, at which time sufficient solution had been ejected from the filtrate receiving vessel into the vacuum trap of an adjacent glove box to cause the excursion to stop. There was no criticality alarm system or other means for alerting the operator or nearby personnel that a criticality accident had occurred. Furthermore, the operators had no criticality safety training. Originally, the circumstantial evidence of the gas release in the filter vessel and the sudden sickness of the operator were puzzling to the operational personnel in the room. The fact that a criticality accident had occurred was determined by a radiation control person called to the scene. Measurements indicated that an intense gamma radiation field was emanating from the filtrate receiving vessel. These measurements were made about 15 to 20 minutes after the accident. The radiation control person immediately ordered a prompt evacuation of the area. About 5.5 hours after the event, the exposure rate was measured to be 18 Roentgen per hour at a distance of 1.5 meters from the filtrate receiving vessel. It was estimated that this exposure rate corresponded to a fission yield of approximately 1 × 10 to the 17 fissions. 17 hours after the accident, measurements of the specific activity in the operator's blood showed 245 becquerel per mil. Based on analysis done at that time, this activity was consistent with an absorbed whole body dose of about 3,000 rad. The operator died 12 days after the accident. 5 other operators had been in the room at varying distances from the reacting vessel at the time of the accident. They received doses estimated to be upwards of 300 rad. All of them suffered from temporary radiation sickness but recovered without apparent long-term health effects. After dismantling the glove box and cleaning the various pieces of equipment, a total of 3.06 kilograms of 235 uranium was discovered in the filtrate receiving vessel. This material was primarily in 2 forms, a thin hard crust due to long-term buildup, and a flocculent precipitate, the concentration of which decreased with height in the vessel. The accident caused no mechanical damage to this vessel, and the room was not contaminated. The glove box was taken apart, cleaned, and reassembled with essentially the original equipment. The operation was resumed after just a few days. During the downtime, a radiation meter was installed on the glove box. Operating instructions were revised, and enhanced operator training was implemented. This accident led to the decision to set up an in-plant critical experiment measurement capability to better determine critical parameters for vessels in routine use. The next criticality accident at Mayak on 2 January 1958 involved this critical experiment setup.